Okay, so back for our last talk today. The pleasure to introduce Guillermo Cortiñas from Buenos Aires, speaking about the algebraic Kirchberg-Phillips problem and twisted Katsura algebra.
Thank you very much for the introduction. I wish to thank the organizers, particularly Peter Hayek, for the invitation to give this talk. So I'm going to start by recalling what the Kirchberg-Phillips theorem says. So the Kirchberg-Phillips theorem pertains Kirchberg algebras. A Kirchberg algebra is a simple, purely infinite unital algebra, which is separable, well, it's a sister algebra. So it's separable, nuclear, in the UCT class. Right, so I highlighted in green the algebraic condition. Okay, and the theorem by Kirchberg and Phillips says that if you have two Kirchberg algebras, A and B, and there are isomorphisms between the K-theory groups, one for K0 and one for K1, then the algebras are Morita equivalent. And if, moreover, the isomorphism at the K0 level carries the class of 1, regarded as an idempotent, matrix, if it carries the 1 to the 1, then you actually have an isomorphism between the algebras. The algebraic Kirchberg-Phillips problem consists in proving an analog of this in the purely algebraic setting. Now, so the Kirchberg-Phillips theorem does not hold, is not stated for all simple, purely infinite unital sister algebras, but for those that satisfy additional conditions. Likewise, one would like to identify some algebraically defined class, say C, of simple, purely infinite unital algebras over a field. So if you have a simple, purely infinite ring, then its center is necessarily a field. So every simple, purely infinite ring is an algebra over a field. So saying that it's an algebra over a field is no restriction, for which an analog of the Kirchberg-Phillips theorem holds. Right, so isomorphism in K-theory implies isomorphism or Morita equivalent or some kind of equivalence. Now, of course, if in the class C I just put one algebra, then the theorem
I have a
will
question.
be
May I?
Yeah, yeah, sure.
You have this green simple purely infinite unital properties because they are, of course, algebraic. But what about UCT? Don't you have some analog, algebraic analog of
Yeah, well, I mean, if you, yeah, well, if the algebra is in, so talking about sister algebras, if the algebra is in the triangulated category, subcategory of the triangulated category KK, the Kasparov category, if it is in the triangulated subcategory generated by the complex numbers, then it satisfies the UCT, right? And you may ask that your algebra in the purely algebraic setting also lives in the triangulated subcategory generated by the ground field within the algebraic KK, triangulated KK category. Actually, all algebras I can handle are of that sort. In any case, the UCT is not the important part because the theorem, the Kirchberg-Phillips theorem, holds also if you, instead of asking that there exists K-theory isomorphisms, you ask that A and B be isomorphic in the KK category, then you don't need the UCT. So it's just the UCT gives you a simpler way of stating the theorem. So are you satisfied with the answer?
Yes, but I don't know what is this category, in triangulated category, in the algebraic case yet.
Yeah. Well, this algebraic KK will appear later in the talk. So
Okay,
I will
thank you.
come to that. Okay. So so of course the class containing just one algebra satisfies this because there's nothing to compare it with. So what one means, one needs some non-triviality assumption. And well, minimally, one would want the Leavitt algebras, which were proved by Leavitt in 1962, at least that's when the paper was published, that they are simple purely infinite. This should be in the class. More generally, those simple purely infinite Leavitt path algebras should also be in C. So that's like a minimal class that one wants to have there. Right. So one thing one could try and do is, okay, so let's see if one can repeat the argument or adapt the argument of Kirchberg-Phillips to the algebraic case. Now, a key to the proof of the Kirchberg-Phillips theorem are the so-called Geneva theorems of Kirchberg, which state absorption properties for Kirchberg algebras. So let's write tensor with the tilde for the sister algebra tensor product. It doesn't matter which, because the algebras I will consider are nuclear. So what happens is that any Kirchberg algebra tensorially absorbs the Kunz algebra O infinity, which is the completion of the L infinity appearing in the previous slide, and is tensorially absorbed by O2. So one could first try and see if an algebraic analog of this is true, whereby an algebra analog, I mean, replace the sister algebra tensor product by the algebraic one, and O infinity and O2 by L infinity and L2. However, this does not hold, as we showed some years ago with Pera-Ara. So what happens is that if you have Leavitt algebras, so P Leavitt algebras and Q Leavitt algebras, and you take the P-fold tensor product of these Leavitt algebras and the Q-fold tensor product of the other Leavitt algebras, and P is not equal to Q, then the algebras are not Morita equivalent. In particular, L2 tensor L2 is not isomorphic to L2, for example, right? And well, the reason for this is really simple. Namely, if you take the tensor product, a P-fold tensor product of Leavitt algebras, you get an algebra whose homological dimension is P. And if you take a Q-fold tensor product, it has homological dimension Q, and if P is not Q, then it cannot be Morita equivalent. Okay, so this first naive approach to the problem doesn't work. But then an idea is to restrict to the case of graph algebras, because for graph algebras, the Kirchberg-Phillips theorem was known before Kirchberg and Phillips, and it has a different proof. So let's start with, so all my graphs today will be finite. If I don't say finite, you assume it is. So it is a finite graph with incidence matrix A. My incidence matrix, I mean, if there are any 0 rows, I delete them. So my incidence matrix is reduced, so it need not be square if the graph has things. It will not be square. And then I take the I, which is the identity if the matrix is a square, and otherwise is the identity with the rows corresponding, or the columns in this case, because I transposed A, the columns corresponding to the things removed. Then for the C-star algebra V, and also for the relative path algebra V over any field L, the K0 of C-star E and LE are equal to an invariant that depends only on E, which I call the Bowen-Franks group of E, and which is the co-kernel of this matrix ME. So they have the same K0s. And the C-star algebra of E is SPI precisely when the Leavitt path algebra is SPI, which is equivalent to a condition on the graph, namely the graph has to have at least one cycle, every cycle has to have an exit, and the graph must be cofinal, which means that if given any vertex B and any cycle C, there is a path that goes out of B and ends somewhere in C. Okay, so the theorem published by Rordan that uses some ideas of Kunz says that if E and F are SPI and the Bowen-Franks groups of E and F are isomorphic, that is the K0s of C-star E and C-star F are isomorphic, then C-star E and C-star F are Morita equivalent, and if, moreover, the isomorphism between the Bowen-Franks groups takes the class of 1, which is the sum of the vertices, to the class of 1, then the C-star algebras are in fact isomorphic. So here we have a condition on K0, and the condition of K1 in Kirchberg-Phillips theorem is not present, but that's just because the K1 of a graph C-star algebra is a free abelian group of the same rank that as the Bowen-Franks group. So an isomorphism of Bowen-Franks groups, that is of the K0s, already implies an isomorphism between the K1s. Okay, so we said before, the first idea was to try and see whether the proof of the Kirchberg-Phillips theorem could be translated algebraically. We saw it cannot. So what about the proof of the Kunz-Rordan theorem? Well, let's review some of the ingredients in the proof of this theorem. Recall, as we said in the previous slide, that the Bowen-Franks group is the co-kernel of this matrix ME. Now, a theorem of Franks says that if E and F are SPI and the Bowen-Franks groups are isomorphic, and moreover, the sign of the determinant of the matrix ME and of the matrix MF are the same. So if the Bowen-Franks groups are isomorphic, then this readily implies that the modules, the absolute values of the determinants of ME and MF are the same. So requiring that the signs be the same is requiring that the determinants be the same. Then these two joint conditions are equivalent to E and F being flow equivalent. Now, this means that you can go from E to F by a sequence of so-called standard graph moves, which I will not list what they are, just that they all preserve both the Bowen-Franks group and the sign of the determinant of the defining matrix. Now, Kunz came up with another move, which we call the Kunz splice, which assigns a graph E minus to the graph E, with the property that it has the same Bowen-Franks group of E as E, but so that the sign of the determinant changes. And here it says F, it should say E minus, sorry. Okay, so here we have the following proposition. The Morita class of C star E is invariant under both standard graph moves and the Kunz splice. So this is the key to the proof of the Kunz-Jordan theorem. So one could try and see whether this holds in the purely algebraic setting. And then we have this result of Abrams, Lowry, Pardo, and Smith, which says that the Morita class of the Leavitt path algebra is invariant under standard graph moves. Notice that the Kunz splice is not one of them. Okay, so this leaves open the question of whether LE and LE minus are Morita equivalent. This is an open question. More specifically, say you consider the graph with one vertex and n loops. Its Leavitt path algebra is the Leavitt ring, the Leavitt algebra we mentioned before. And let us write Ln minus for the Leavitt path algebra of Rn minus. So in the particular case, the previous question in the particular case of this particular graph is also open. It is not known whether Ln and Ln minus are isomorphic or equivalent or Morita equivalent. And if notice that, it is easy to see that the Bauer-Franks group of R2 and of R2 minus are both 0, right? So an isomorphism between the zero groups is 0. So it takes the class of 1, which is 0, to the class of 1, which is 0. So if the algebraic analog of the Kirchberg-Phillips theorem or the Kunz-Jordan theorem were true, then one would necessarily have L2 and L2 minus being isomorphic. So L2 and L2 minus, if this is going to work, should be isomorphic. And well, this is open, whether such isomorphism exists, but there are some results which point in the negative direction. So for example, we have here this result of Johansen and Sorensen, which says that there is no star algebra isomorphism between L2 and L2 minus that is defined over the integers. So you can take the Leavitt path algebra of a graph over any ring, and if you just allow integer coefficients, then by this result, there is no isomorphism, which in addition preserves the involution.
Sorry, before you switch slides, may I ask you some questions? One is, would it be easy to draw for us this, say, R2 minus graph, so we know how R2 looks like, right? How about our R2 minus? Is it something very difficult to draw?
Well, let me see. If you wait a second,
Sure.
Let me see. I have here. Ufa.
You have it drawn somewhere.
Yeah, I have it doing somewhere, which is what I'm trying to find. Here it is. Yeah. So am I sharing this?
Yes, yes, we see it, yes.
Yeah, okay. So this is the graph. So given a graph E, and the vertex, so the vertex, the dot, the black dot, should be in some cycle, and then you add that picture. In terms of the matrix, of the incidence matrix, what you do is you add these 2 rows and 2 columns to it. which make the determinant change, the sign of the determinant change.
Yeah, this is great. Thank you very much. This really helps.
Okay.
And next, is it possible that you have such a situation that the Leavitt-Path algebras are not Morita equivalent, but you take their C-star completions, you talk graph C-star algebras, and they are Morita equivalent in the C-star sense? Is it possible or not?
Well, I mean, we know
You
that
achieve this
ln
equivalence only after completion, is it?
I mean, we know that the ln and ln, that On and On minus are Morita equivalent in the C-star algebra setting, and we do not know whether they are
At the Leavitt.
whether ln and ln minus are.
Okay.
Right?
Okay.
So,
Okay. Yeah. I good. Thank you so much.
okay. Right. So, so I was saying, well, this is, I view it as a negative result. Of course, I mean, if this does not say that there is no algebra, star algebra isomorphism between L2C to L2C, where C is the complex numbers, not Z, right? Or even with Q instead of Z. Right. Now, also, if you ask the homomorphism, the isomorphism to be graded, to be homogeneous with respect to a grading, then there's also a negative result. So, and the Leavitt-Path algebra is graded over the integers, which for the purpose of the current slide, I will call C infinity. And once you have a set grading, you have a set mod M set grading for any M, in which the part of the homogeneous component of degree I, where I is a remainder in the division by M, is the sum of all the homogeneous components corresponding to N's congruent to I mod M, right? And so you may ask whether there is an isomorphism between ln and ln minus that preserves any of these gradings. And we showed with my student Guido Arnone that if L is either a field or a PID, such as the integers, n is bigger or equal than 2, this n will go for the Ln. These are the n's for which Ln is simple purely infinite. L1 is the Laurent polynomials, which is not simple. And M, which will go for the grading, it goes between 2 and infinity. Then there are no unital CM homogeneous homomorphisms between Ln and Ln minus, nor in the opposite direction. Okay, so not only they are not isomorphic, they don't talk to each other. I mean, there is no map between them that preserves the unit at least, and also any of these natural gradients. So of course, this doesn't mean that Ln and Ln minus are not isomorphic. They could be could still be isomorphic in a non-graded way, and in a way that does not preserve the star, or does preserve the star, but is not defined over the integers. Okay, so this does not solve the problem. It simply indicates that if there is such an isomorphism between L2 and L2 minus, it will be very strange in some sense. I mean, at least it points in that direction. Okay, so what if one reduces one's aspirations, and instead of asking for a classification up to Morita equivalence or up to isomorphism, one asks for a classification up to homotopy. So here homotopy is as follows. So I take two algebraic homomorphisms. I say that phi and psi, I declare them to be homotopic. If there is a sequence of homotopies connecting them, and a homotopy is a homomorphism from A to the polynomials on B, such that when you evaluate at 0, the first homotopy, you get the first homomorphism. When you evaluate at 1, the last homotopy, you get the last homomorphism. And in the middle, the evaluation at 1 on the ith homotopy takes you, is the same as the relation of 0 at the I+1 homotopy, right? So a homotopy is so a homomorphism from A to B at T is a homotopy between evaluation at 0 composed with the homomorphism and evaluation at 1 composed with the same. So you can, this says that you can reach from, you can go from phi to psi by a finite number of these steps. Okay, so we showed with my former student Diego Montero that if E and F are SPI, finite SPI graphs, and the Bauer-Franz groups are unitally isomorphic, then there exist unital homomorphisms in both directions, such that both compositions are homotopic to the respective identity maps. So in the presence of, under the hypothesis of the Kunz-Rordan theorem, we get not isomorphism, but unital homotopy equivalence. It should be said that both in the Kirchberg-Phillips, in the case of the Kirchberg-Phillips theorem, and the case of the Kunz-Rordan theorem, they first prove that well, they first show an equivalence like this in the C-star algebraic setting, and then they show that if one has a homotopy equivalence, then using some analytic trick, you can get an actual isomorphism. Yeah. And this is the part that does not, that we, I mean, at least I have no idea how to reproduce in the purely algebraic setting, but at least we can get up to the homotopy classification.
Sorry,
And
may I ask a question?
Sure.
Why are using small letters, small characters for SPI? Is there some subtlety of?
No, simply, I mean,
it was the same.
In the previous slides, I used capital.
Yeah.
Yeah, well, no, it you know.
Okay, it doesn't matter.
It shortened.
Good, thank you.
It got pressed. Okay, right. And so the next result relates this algebraic homotopy classification result with the Kunz-Rordan theorem in the C-star algebraic setting. So it will involve homotopy in the usual sense of C-star algebras, which I will denote by this double thing. Okay, double equivalence. Okay, so if E and F are SPI and we have a unital homomorphism between the C-star algebras of E and F, then there exists a unital star algebra homomorphism between the Leavitt path algebras of E and F over the complex numbers, such that when you, I mean, because this phi is unital and is a star homomorphism, because it's a star homomorphism, it passes to the completion. And this is the hat, this is the phi hat. Okay, so any unital star homomorphism between the C-star algebras is homotopic in the continuous C-star sense to the completion of one that is already defined at the C-star level, at the Leavitt level. So it's always, I mean, LC of E lives inside C-star of E. So you always get a map when you have Xi, you have a map from LC of E to C-star F, right? So the problem is to have it land in LC of F. And you can get that up to homotopy. Moreover, if the Xi you started with is a homotopy equivalence as a mapping between C-star algebras, if and only if the phi is a homotopy equivalence in the algebraic sense described above. Okay, so in particular, say the Bauer-Franz groups of E and F are isomorphic in a way that carries the one to the one, the unit to the unit, then by the Kunz-Rordan theorem, C-star E and C-star F are isomorphic. And in particular, this isomorphism is a homotopy equivalence. So the homotopy equivalence by this result is homotopic to the passage to complete, the map obtained by passage to completion of a homotopy equivalence, the homotopy equivalence given by the theorem above. Okay, so the theorem above gives you a map, which when you complete, gives you a homotopy equivalent to the isomorphism that the Kunz-Rorland theorem says exists. Okay, so in this sense, there is a nice correspondence between this result above and the Kunz-Rorland theorem.
Sorry, question again.
Yes.
Is SPI assumption necessary for the first sentence in this theorem?
Yeah, because so what I get is a functor from KK algebraic to KK, well, I mean, to the full subalgebra, the full subcategory of KK algebraic whose objects are the Leavitt path algebras of finite graphs, to the Kasparov KK category. And I compare KK, algebraic KK of the Leavitt path algebras with Kasparov KK between the graph sister algebras. And what I use is that if the graphs E and F are SPI, then in both cases, the KK class is the same as any KK. So KK of A, B, for A and B, Leavitt path algebras, or for A and B, graph sister algebras that are SPI, and so corresponding to SPI graphs, this coincides with the sets of homotopy classes of algebraic homomorphisms. So that's why I need E and F to be SPI. Otherwise, I would get a statement about homomorphisms in the KK category. So I'm using that homomorphisms in the KK category when the algebras are Kirchberg, say, is the same as homotopy classes of actual sister algebra homomorphisms. And an analogous result for algebraic KK, at least between SPI Leavitt path algebras. Did I answer
Yes,
your
thank
question? Okay. Okay, so this is all I have about the particular case of the Kirchberg-Phillips problem that pertains Leavitt path algebras. Now, what about more general algebras? Because you see, okay, so let's examine the situation. So here we have a finite graph E. And so I will, yeah, because okay, so I go to Katsura algebras. So Katsura, so an important thing is that since I don't have, I mean, the Geneva Kirchberg's Geneva theorems do not hold in the algebraic setting. What I need to be able to work with my algebras is some combinatorial description of the algebras by generators and relations. Okay, and well, such algebras are the Katsura algebras. So let me recall how they are defined. So one has a finite graph E, and with incidence matrix A, indexed by the reg E means the regular vertices. Since E is finite, that means those vertices that are not sinks. And then I write B1W for the set of all edges whose source is B and whose range is W. And I number them from 0 to, well, I mean, they are as many as ABW. And I label them from 0 to ABW minus 1. Then you bring in another matrix, which may have negative coefficients. It has to just have integer coefficients. I must have the property that if a particular coefficient of the matrix A is 0, then so the same is true for B. And given this setup, you can define an action of the integers on the set of edges that preserves the endpoints and which acts by translation. So you look just at the numbering that the edge has, and you shift that numbering by as indicated by the corresponding coefficients of the matrix B. So this sum there, this I plus BBW, is to be taken modulo ABW. Okay, so that defines an action of, that gives you an automorphism, which defines an action of a graph automorphism of B, which defines an action of the integers on the graph. And associated to that action, you have a one cocycle, which is this phi. This letter Q indicates the quotient in the division. Okay, so you take I. You take I, which corresponds to the edge EI, and you apply the action sigma n times. So you get I plus NBBW, but not modulo A, but you do this in Z. And now you take the quotient of this integer in the division by ABW. That's what the cocycle phi of NE is. This E should have an I there as a subscript, which I omitted. Okay. So I thought I wouldn't have any corrections to make to the slides before sending them to you, but now I see I do. Sorry about that. Okay, so the Katsura algebra, sister algebra, and the Katsura plane algebra of the associated to the matrix is A and B is the Excel-Pardo sister algebra of the triple E sigma phi. So, here I am cheating because Excel and Pardo paper came later than Katsura's. Katsura's paper dates back to 2008. And the Excel Pardo paper is from 2017. Okay, so what the Excel Pardo do is given an action of a group on a graph by group automorphisms and a cocycle with respect to that action with values in the group, they build a self-similar action of the group on the set of paths, and out of that, they construct a sister algebra by generators and relations. The same generators and relations, if you do not complete and consider them over a field L, not necessarily complex numbers, then give you an algebra which I call OAB, which they also consider, and it's this purely algebraic object is also considered in a paper by Katsura, Pask, and well, I had prepared a little piece of paper with a list of the names of the authors of all the papers, but then now I lost it as I would. Anyhow, so Hafrat and Pask are, and Sims and Sirakovsky, I think it was the other one, are behind these H, P, S, and S letters. Okay, so these are the Katsura algebras and the algebraic counterpart. And I will say that a pair AB as above is K SPI, K for Katsura. So this means that it satisfies the Katsura conditions for simple purely infiniteness. If, first of all, the graph is regular, second of all, A is irreducible, which means that some power of E has all positive entries, that that in the graph, every vertex is the basis of at least two loops, that the diagonal of the matrix B consists of ones, and that's the condition. So Katsura showed that for any A and B, for which the sister algebra, sister AB is defined, the sister algebra is separable unital nuclear and in the UCT class. So if you add that it be simple, it will be a Kirchberg algebra. Now, he, for any A and B, computed the K0 and K1. Notice, by the way, if B is the zero matrix, then C star A is the same as the C star algebra of the graph E. And similarly, OA is the David path algebra of the same graph. And then you get the kernel of, and then if P is zero, you recover the usual, the known K0 and K1 of the C star algebra of the graph, right? And then you have these two other terms. And moreover, he showed that if A and B are ESPI, are KSPI, so they satisfy the Katsura conditions for simple purely infiniteness, then the C-star algebra is SPI. And moreover, so in particular, it is Kirchberg. And moreover, if A is a Kirchberg algebra such that its K-theory is finitely generated as a group, then the algebra is isomorphic to one of these Katsura algebras that are associated to a pair AB that satisfies the Katsura conditions for simple purely infiniteness. Okay, so the conditions, the KSPI conditions are not, and if, I mean, are sufficient, but not necessary to get that the algebra be simple purely infinite. In fact, Excel and Pardo characterized, assuming, so this Katsura algebra, more generally the Excel Pardo algebras, have a groupoid model. So they are the sister algebras of some groupoid. Assuming that the groupoid is Hausdorff, Excel and Pardo characterized the matrices A and B such that the Katsura algebra associated to that pair AB is SPI, and they are more general than the Katsura conditions. But Katsura conditions sometimes yield algebras that correspond to groupoids that are non-Hausdorff. Okay, but at any rate, the Kirchberg theorem and the Katsura theorem, the part 4 of this theorem, together with the Kirchberg-Phillips theorem, tells you that if you have any other SPI Kirchberg algebra, for example, the C star of AB with AB satisfying, I mean, it doesn't matter whether it satisfies the KSPI conditions. If it happens to be simple purely infinite, it will be isomorphic to some C star A prime B prime, where A prime and B prime do satisfy the Katsura SPI conditions. Okay, so they are quite general. Okay, right. And so the importance of this is, well, so if I this tells me that suppose I can prove an analog of Kirchberg-Phillips at least up to homotopy for all algebras OAB such that the AB satisfies the Katsura SPI conditions. Then I will have proven it. This class will contain as many algebras as the Kirchberg algebras whose K-theory is finitely generated. So it's a rather large class, an interesting class to try one's tools at. Okay, and let me explain a bit what Katsura does. One can look at C star AB in the Kasparov category. So I will write C-1 for the suspension, that is the continuous functions on the interval that vanish at both endpoints. By the exponential map, this is isomorphic to the kernel of the evaluational one coming out of the continuous functions on the circle. And therefore, you may, so because this evaluational one has a splitting, you can write the continuous functions on S1 as C plus C-1, right? Okay. So there is a Toeplitz extension, completely analog to the Toeplitz extension of the C star algebra of a graph. There are, so in the conditions defining C star AB include the graph algebra conditions. So in particular, they include Kunz-Krieger condition 1 and Kunz-Krieger condition 2. So if you omit Kunz-Krieger condition 2, you get the Toeplitz algebra, right? And so you get the presentation of the C star algebra of AB as a quotient. And now this extension, you may regard this, look at this extension in KK. So Katsura shows that it identifies this with, if you want, with sums of copies of the continuous functions of the circle, because C plus C-1, we said, is isomorphic to the continuous functions on the circle. And there is a map F, which is a map in KK between these two, so which corresponds to the inclusion of K into T, but so it's class at in KK. And recall that, well, KK of C-1, C-1, because C-1 is a suspension, which is a category equivalence, is the same as KK of CC, which is the K0 of C, which is the integers. And so it makes sense to say that F is this matrix. So what do I mean? So in this matrix, I am thinking that the composition I'm looking at is, I wrote C plus C-1 to the reg E. So I think of this as C to the reg E plus C-1 to the reg E. And similarly with C and plus C- to the E0. So a map has a natural matrix decomposition with respect to that direct sum decomposition. And so this 1 minus AT is a map in KK between C to the reg E to C to the E0. Similarly, 1 minus BT is a map between C-1 to reg E to C-1 to E0, right? Okay, so that's what Katsura identifies, and this is how he gets his calculation of K0 and K1 of C star AB. And right, and then one can, one had these isomorphisms, and so one can replace K and T by these sums of copies of C plus C-1. Right, that's what I wrote. And when you take an algebra extension of sister algebras and you look at it and KK, you get what is called a distinguished triangle in the triangulated structure of KK, which means that if you home it on any side, you get, that is, if you apply the KK groups, on any side you get long exact sequences, which since both periodicity tells you that if you apply suspension twice, you get the identity. So you get the long exact sequences are not so long. They are six. They have 6 terms. But anyway, we have such a triangle, and observe that the zeros in the off-diagonal terms are necessarily like that, because they correspond to maps between C-1, sums of copies of C-1, and sums of copies of C, or conversely from sums of copies of C to sums of copies of C-1, and the homomorphisms in KK between those things are 0. So there is no other possibility. And so that is, in every KK triangle, the map G, as shown there, the map G has to have a decomposition like that, where the off-diagonal maps, with respect to the matrix, the form that I said before, have to be 0, right? So G must have diagonal block form. What Katsura does, if he shows that if N and M are in the triangle above are equal, then it is possible to choose a larger N and a pair of Katsura SPI matrices of size big N, such that there is a triangle with the same A we had before, and such that F is as before. That is, it's 1 minus AT, 1 minus VT. So by 5 lemma kind of argument, one concludes that A is isomorphic to C star AB, right? This is the argument. So this holds for any C star algebra A that admits such a triangle, right? And okay, so if A it says if A is Katsura, if A is Kirchberg, it should say. If A is a Kirchberg algebra, and then since C star AB is also a Kirchberg algebra, and well, so they are isomorphic in KK, then the K groups are isomorphic, and therefore by the Kirchberg-Phillips theorem, they are also isomorphic as C star algebras. Okay, so that's how he shows that the Kirchberg algebras are with these finitely generated K groups are Katsura C star algebras. Okay, so yeah. So what about algebraic KK? So out of respect, my algebraic KK is with lower case. This is indeed intentional. So I fix the field L and write OAB for OAB, the Katsura algebra over L. And the first thing one can show is that there is a KK triangle, just as the one we had before, coming from an analog of the Teplitz extension we had before, with the same, where F has the same form as before, right? But this, it's not as satisfactory as before, because, okay, so this makes sense because KK of LL and KK of L minus 1, L minus 1 are both the K0 of L, which, if L is a field, is the integers, so that makes sense. But the zero, the off-diagonal 0 terms, they can be 0, of course, but they are not the most general that can be. They don't give the most general kind of morphism that can be, because kk of L minus 1 L is L star, is the multiplicative group of L, right? And so there could be in the upper right block, there could be a matrix with coefficients in L star, right? Of course, this 0 is the neutral element of L star, so to speak. I mean, it should be a 1, but it's the one that is the neutral element of L star. On the other hand, the 0 in the block, in the lower left block, is okay. It's the most general it could be, because k minus 1, this gives you k minus 1 of L and k minus 1 of a field, actually k negative of a field is 0. Hence, if you have any kk class, so any homomorphism in the algebraic kk category between L plus L minus 1 to the m and L plus L minus 1 to the n, it must have a form, a upper triangular form like that, where m and n are matrices with integer coefficients, and P is a matrix with coefficients in L star. Okay. Okay. So, okay, this tells me that I should consider algebras that are a slight variation of the or not so slight of the Kunz algebra, the Katsura algebras, such that when I compute them in kk, I get a p up there, right, in the upper right block. And this is how we come to the twisted Katsura algebras. So we consider a finite graph E with incidence matrix A and a B, just as before, and now we add a C, which has coefficients in the multiplicative group of the field. Required in the same conditions as above between A and B, and with the additional condition that the C, I mean, so if A is trivial, then also so are B and C. Now for C, being trivial means being 1. Now, using C, one can define a cocycle from C times C1, the edges, to L star. And then with this cocycle and the Katsura cocycle phi that you had before, we generate a new cocycle, which now takes values in the Laurent polynomials. So, which are the group algebra of the integers over L. And how you do that? You just multiply the two cocycles, right? So this lands in the units of this ring. And the twisted Katsura algebra is, which can be regarded as a twisted Steinberg algebra. So as I mentioned before, whenever you have a Excel-Pardo triple consisting of a group acting on a graph and then a cocycle, you have some associated to it, you have a groupoid, and you can look at the sister algebra, at the Steinberg algebra of that groupoid, and you can twist it. So twisted Steinberg algebras were studied among other places in this paper, which has many authors. One of the first of them being Armstrong. Okay, I have the list at the end of the slides. Okay, so this gives you a new algebra, which I call OABC, which is associated to E, sigma, and this cocycle psi that I wrote above. And then one can show that there is a triangle in KK, again coming from an analog of the Teplitz extension, where F has this form, where, I mean, you expect to have, I mean, we have 1 minus AB transposed, right? And now we have 1 minus ACB transposed, where minus, in the case of C, is taking the inverse of each of the coefficients and transposing it, right? So this is what we have there. Okay, so now this is sufficiently general, right? And okay, so what I can show is the following. So if L is a subfield of the complex numbers and AB satisfies the Katsura conditions for simple purely infiniteness, then the twisted Katsura algebra is simple purely infinite. Here I use I use some results of Clark, Excel, and Pardo, which they have come up with a sufficient and necessary condition that for a groupoid, not necessarily Hausdorff groupoid, to have a simply purely infinite or simple Steinberg algebra, right? And well, I use, and the same for the sister algebra of the groupoid. And I use that and the fact that the Katsura sister algebra of AB is simply purely infinite when AB is KSPI. To conclude this, that's why I need that LB is a field of the complex numbers. If I add that the groupoid be Hausdorff, then I can use the paper on twisted Steinberg algebra as mentioned before to conclude again that O is SPI, and then I do not need that LB is a field of the complex numbers. But if I wanted to hold for any AB such that AB is KSPI, then I need L to be as a field of the complex numbers. Okay. So, moreover, if N is bigger than 1 and R is an algebra that admits a presentation like this in KK, then there exists an N bigger than N, an A and B matrices of size N, and A bigger than with A non-zero, so that, I mean, N non-negative, so that it can be the incidence matrix of some graph, and C a matrix with coefficients in L star, such that the pair AB is KSPI, and so that OABC is isomorphic to R. Okay, so what I'm saying is that any algebra R that admits such a presentation is isomorphic to a twisted Katsura algebra that is SPI. Okay, and okay, so if R were already a Katsura algebra, a twisted Katsura algebra, and that is SPI, and if the theorem of Kirchberg-Phillips were the algebraic version were true for twisted Katsura algebras, then I would have that R and OABC are isomorphic as algebras. Okay, but I don't have that still. I aspire to have an isomorphism up to a homotopy equivalence, but I still do not have it. I'm working on this. Okay, so here are the references. The ACC plus 22 is this paper by Armstrong, Clark, Kearney, Lin, McCormick, and Ramage. Okay. This CEP paper is, I think it's a very important paper by Clark, Excel, Pardo, Simpson, Starling, which solves the problem of simplicity for algebras associated to non-Hausdorff groupoids. And yeah, well, there are several there. The comparison, I mean, this thing that shows the correspondence between a result on homotopy classification in the algebraic setting and the original Rordan theorem is the first of the papers is in this slide. And these are the classical Kirchberg-Phillips and Rordan papers. Okay, thank you. That's all I had to say.
Thanks, Guillermo. Are there any questions? Or questions from online? So I have a wishful thinking kind of question.
Yeah.
But this is going back to the first part of your talk when you were discussing ln and ln minus.
Yeah.
Of course, for example, for ON, there are many different ways of writing ON from a directed graph. And if you allow infinite directed graph, well, of course, even more ways of doing it. And I wonder, now, of course, you can always just stick on this extra bit that you can splice any graph. Like generating something very equivalent to ON. But I wonder, first question is, have infinite graphs in the Levitt path algebra situation been studied at all? And if so, maybe you could construct one read equivalent to ON in such a way that you can absorb the proof splice and tell you something about Morita equivalence of Levitt path algebra. If that makes any sense.
Well, I mean, there is a classification result for Levitt path algebras of graphs having, I think they require that all vertices are infinite emitters, which is like a dramatic version of what you're saying.
Yeah, it's a little restrictive if you want to build something that doesn't.
I cannot hear you properly.
Okay, sorry, I see. I didn't have this close enough. No, sometimes you can build a graph that will do something that you want in terms of K-theory or some other properties by just adding more and more stuff. And if you allow yourself an infinite graph, you might be able to achieve something. But if you insist on having always infinitely many edges between pairs of vertices that have edges, that maybe is too restrictive to build something with a certain property. But I just wonder if you know.
So you mean like the singularization?
Yeah, I just so it's like an ad hoc thing of just trying to,
Yeah. So well, the problem is, I mean, if you so this argument of Morita, I mean, of homological dimension, tells you that, I mean, if you want to add more things but keep in the same Morita class, then you are not going to fix the problem, right?
oh, okay, something more rigid in this algebraic setting.
Right. Yeah. So, well, I read. So one project I took over at some time ago was, well, let's see if I can, well, I mean, without, I know they are not isomorphic, but maybe one can play around with tensoring it. I mean, if maybe it's a matter of like you need to, I mean, if you have L infinity tensor A, you get A, okay. But if not, you get L infinity tensor A. And then tensor at many times as necessary and follow the proof of the Kirchberg-Phillips theorem. But then I found that it is necessary. I mean, you cannot do without this isomorphism. So, I mean, I tried to see if there was a way around this. but couldn't find it, and so I abandoned that line. But yeah, maybe someone comes up with a better argument with no idea. Also for the L2 isomorphic to L2 minus, I mean, I know people who believe that it can be true, but it's a hard problem. So, I mean, homotopy is much easier. So,
Okay, thanks. Yeah, it was a nutty idea anyway.
May I ask you some non-mathematical questions?
mhm.
So one is about this paper solving simplicity problem by, you said it was very important by Aidan Sims and many other people. I noticed there was only archive reference from 2018, so it wasn't published yet.
Well, not as far as I know, but I mean, let me. Wait a sec. So I would go to Rui's webpage and see. Okay, so see non-Hausdorff. Well, no, this is not it. Non-Hausdorff. Let me see. Yeah, well, yeah, no. It's published already. Yeah,
Okay.
it's in the transactions.
Okay. Very good.
Yeah.
Very good. I will just.
Yeah, good point. Good point.
Okay. And my second question is even worse. I simply couldn't resist during your talk examining the contents of your shelves. And is it possible that there's no mate? I cannot find mate anywhere. I'm looking very carefully and I cannot see any
No, well,
mate.
there is no, the mate is in the next room.
Ah, okay.
I mean, there is a thermos here,
Okay.
and there is yerba. So you
Okay.
see, this is what you put into mate.
Ah, okay. Okay, excellent. Excellent. So
But
at least-
yeah, but the one who drinks mate mostly is my wife, and I prepare it for her. I myself don't drink as much mate.
Okay, thank you so much.
Okay, so it's been a pleasure.
Yeah, thank you. We really
Um,
appreciate it. It was
okay.
great having you around.
Okay, thank you. Bye-bye.
Let's thank the speaker again.
Thank you.